In this lesson, Trends in the Periodic Table, we're going to look at different properties of atoms, like their size, their ionization energy, their electron affinity, their electronegativity, and their reactivity. And we're going to use their atomic structure in order to understand the periodic trends and variations of these properties within the elements of the periodic table. A few concepts that are important that will have an impact on the properties that will help us to understand the properties are the shielding effect and the effect of nuclear charge. The shielding effect is that dealing with the fact that as electrons are farther away from the nucleus, so for example, these electrons here in fluorine in the second energy level, are shielded from the attractive force of the nucleus because of the inner shell of electrons. So the farther away the electrons are and the more shells there are between the nucleus and the electrons, the greater the shielding. The effect of nuclear charge takes a look at the charge that is felt by an electron, and it takes into account the repulsive effects of the electrons, so the shielding and also the electrons within their own energy level, as well as the nuclear charge. So we're going to use these terms in explaining the trends in the periodic table of the different properties. The first property that we'll look at is atomic size. And the atomic size as you're going down a group, the atomic size increases. And as you go across a period, the atomic size decreases. In order to understand that, if we look at a periodic table with Bohr models of the atom, we can see the periodic trend. So as we're going down a group, so in this case from hydrogen to sodium, each time we start a new row or a new period, we introduce a new energy shell. The principal quantum number of the valence electrons is increasing as we go down the group. And so as you can see, the electrons are progressively farther away from the nucleus, and the electron shielding is increasing as we have more electrons between the nucleus and that valence electron. So it's natural to see that the atoms are getting larger as we go down a group. Going across a period, the trend isn't quite as obvious because it's natural for people to think that if you're adding more electrons to the atom, then it's going to get larger. But what we actually need to look at in this case is the effect of nuclear charge. As we're going across a period, we're adding electrons to the same energy level. So in the second row or period of the periodic table, each of the electrons that are added as we go across are added to the second energy level. Every time we add an electron, though, we also add a proton to the nucleus, which is increasing the positive charge on the nucleus. And protons, being much heavier, are going to have a greater attractive force than the repulsive force of the electrons that we're adding. So as we go across, because the nuclear charge is increasing, there's a greater attraction by the nucleus to the electrons. And so what happens is the electrons get pulled tighter to the nucleus, and we're slightly getting smaller as we go across. What's important to note at this stage for all the properties is that there's greater increases or changes going down a group than we have as we're going across a period. So the changes in the atomic size going across are a bit more subtle than they are as we're going down a group. Now, in discussing atomic size, what we can also look at is the size of an atom compared to its ion. So we need to look at this in two separate categories. We need to look at atoms that become cations and atoms that become anions. So when we add an electron and form an anion, so in the example of fluorine, which has 7 valence electrons, and gains 1 electron to become F minus, an anion, as it forms an ion, the size of the ion in this case is going to be larger, because by adding an electron to the second energy level, we've increased the repulsions of the electrons, and so overall the effective nuclear charge has decreased. When the effective nuclear charge decreases, the atom gets larger because the nucleus is not pulling the electrons in as tight as it previously was. So when comparing a fluorine atom to an ion, the ion is larger. In looking at cations, an example is lithium. Lithium has 1 valence electron and becomes lithium plus after losing 1 electron. When we look at this, we can see that by losing that 1 electron, we've lost an entire energy level in this particular species. So we can see quite clearly that the ion is going to be smaller. In addition to losing an energy level, we've also increased the effective nuclear charge because we've decreased the repulsions of the electrons. The next trend that we'll look at is ionization energy. Ionization energy is the energy required to remove an electron from the valence shell of an atom. If we want to look at this as a little chemical reaction, for the atom A, if we add energy, we'll be able to remove an electron. If we remove an electron, A becomes A plus, a cation, and then we've got a free electron left over. Now the trend for ionization energy, as you go down a group, the ionization energy decreases. As we go across a period, the ionization energy increases, meaning that it takes more energy to remove electrons from the noble gases than it does from the alkali metals. So if we look at the periodic table, we can explain the trends. So going down the group, as we saw from the trend, it decreases. So it requires less energy to remove an electron from a sodium atom than it does from hydrogen. As we're going down the group, as you have seen from the atomic size, the valence electrons are in energy shells farther away from the nucleus, which means there's an increase of shielding of the inner electrons. This increased shielding blocks the attractive force, or shields the attractive force, of the nucleus on this outer electron. So therefore, this electron in the outer shell is more loosely held than one that's closer to the nucleus with less shielding. So farther away it is, the easier it is to remove it from that valence shell. Going across the period, as we saw, the atomic size decreases as we go across because of the increase in the effective nuclear charge. So what this means is that the electrons that are being removed are closer to the nucleus. They have a greater attractive force to the nucleus, and so they're going to be much more difficult to remove. When we talk about second ionization energy, the second ionization energy is the energy to remove the second electron. So we have an ion. If we want to look at it as a reaction, we have an ion, like A+, and we're adding energy, and we're going to remove an electron, so we'll be left with a 2+ plus an electron. Now, the second ionization energy is always going to be higher than the first ionization energy, regardless of the atom that we're examining, because by removing an electron, we've increased the effective nuclear charge in that particular species. So the ion is always going to have a higher effective nuclear charge than the atom that it came from. Now, in terms of second ionization energy, the trend does change because the alkali metals actually have the highest second ionization energy. After lithium or sodium have lost one electron, they've lost an entire shell, and now they have quite a stable ion. So the electrons are held quite tightly to the nucleus. The shielding has been reduced, the effective nuclear charge has increased, and so it's much more difficult to remove the second electron from an alkali metal. So for that reason, these have the highest second ionization energy. For the trend, what you need to do is visualize the alkali metals being moved now to the right-hand side of the noble gases, and then the trend is, as it was before, increasing from left to right. So the alkaline earth metals have the lowest second ionization energy, and the alkali metals will have the highest. The next property that we'll look at is electron affinity. Electron affinity and electronegativity are the next two that we're going to look at, and they are connected and related to one another, and we'll discuss that when we begin our discussion of electronegativity. Electron affinity is connected to ionization energy because it is the exact opposite. Ionization energy was the energy required to remove an electron, while the electron affinity is the energy released when an atom gains an electron. So in looking at the reaction, we have an atom. This time the reactant is an electron. So we're going to capture this electron to form A minus, and that's going to release energy. Now, the reason that energy is released is because if you think about this high energy electron, so say, for example, on its own, the electron has 800 joules. And this is just for example's sake. This wouldn't be the exact amount of energy by any stretch of the imagination. Okay, so if it has 800 joules on its own, when it gets captured by an atom, it's going to be attracted to the nucleus, and so its energy of this free electron is going to get lower. So if we start with an electron at 800 joules and it gets captured by an atom and its energy is lowered to 100 joules because of that attraction, then there has been a release. There's all this excess energy that gets released, and that's 700 joules. So in thinking about this as a concept, the greater the attraction that the atom has for an electron, the more energy will be released. Because the greater the reduction in the energy of the electron, the more energy is going to be released. Now, when you look at the periodic table for this trend, you can see that the noble gases have not been included. And that's because they don't tend to gain electrons. For this trend, the electron affinity is going to decrease as we go down the group, and it's going to increase as we go across a period. So as we go down a group, what we need to do is look at where this electron is being added. The electron is being added progressively into a farther energy shell from the nucleus. So there's greater shielding from the inner electrons. So that electron that's being added is not going to have as great of an attraction to the nucleus. So an electron added in lithium is going to have a greater attraction to the nucleus than an electron added in sodium. For that reason, less energy will be released when that electron is captured by the atom. Going across a period, We're adding electrons to the same energy level, so there's about the same shielding from the inner electrons. The key here is the fact, again, that the nuclear charge is increasing as we go across the period. Because the nuclear charge is increasing, there's a greater attraction to the nucleus by the electron, and so therefore more energy is released because of that greater attraction. So as you can see, there's a pattern developing. When we want to examine a trend going down a group, we need to look at the energy levels that exist. And when we're examining trends going across a period, we need to look at the nuclear charge and the fact that it's increasing as we go across the period while the electrons are being added to the same energy level. Electronegativity is our next trend, and it follows the exact same trend as electron affinity. So it's going to decrease as we go down a group, and it's going to increase as we go across. What electronegativity is the relative attraction that an atom has for electrons. So electron affinity had an energy value. It was exactly the amount of energy that's released when the electron is gained by a particular atom. With electronegativity, when we say that it's a relative number, it's a tool that we use for comparing atoms. We're going to be using electronegativity in our next unit to help us to examine bonds. For now, we need to recognize it as a property that's been assigned with relative numbers. So for example, fluorine has an electronegativity of 4.0, and sodium might have an electronegativity of 1.0. These numbers don't have a unit, they just show the relative attraction that the atoms have for electrons. So in seeing those values, we can tell that fluorine has a greater attraction for electrons than an atom of sodium does. The trend is exactly the same as electron affinity because the greater attraction that an atom has for electrons, the greater the energy that will be released when an electron is actually gained. So the property trend is the same, and the explanation for the trend is the same because they are so interconnected. The difference really lies in the fact that electron affinity is an energy value and electronegativity is a relative value. The last property that we'll look at is the reactivity within a family. We're going to look at the reactivity of the metals, specifically the alkali and alkaline earth metals, and we're going to look at the halogens. When you want to look at the reactivity, what we need to do is look at what these atoms will do during a chemical reaction and look at what property will help us to explain the reactivity. So an alkali metal, something like lithium, has one valence electron and wants to lose that electron to become a cation. So when we want to look at the reactivity of lithium compared to the reactivity of sodium, we need to compare their ability to lose that electron. So the trend for ionization energy is going to really help us. As we go down a group, the ionization energy decreases, the ability to lose an electron increases, and therefore the reactivity is going to increase. The more loosely held the electrons are, because of the size of the atom, the more easy it's going to be to remove the electron, and therefore the more reactive it is. The trend is similar for the alkaline earth metals. They are trying to lose electrons, so it's the ionization energy that's going to help us to explain the fact that as we go down the group, the atoms are going to become more reactive. These are slightly less reactive than the alkali metals because they have 2 electrons to lose, however. We can have a similar discussion for halogens. Looking at halogens, we've got fluorine, bromine, iodine, and chlorine. They want to gain electrons, or they do gain electrons in their reactions. So in comparing the reactivity, what we want to do is compare their electron affinity. Chlorine has an electron affinity that is lower than fluorine. Fluorine being the smallest in the group, it's going to have the greatest attraction for electrons and therefore release the most energy. So, in this regard, fluorine is more reactive than chlorine. So alkali metals and the halogens, the metals and the nonmetals, have opposite trends in their reactivity. For alkali metals, it increases as you go down. For halogens, it increases as you go up from bottom to top. That concludes our discussion of the trends within the periodic table. And the practice questions in the textbook will help you to put elements in order based on the different trends that exist within the periodic table.